Welcome to the Inomena video tutorial about concentrating solar power. This lecture is about the fundamentals of the Stirling systems. My name is Wolfgang Reinhalter. I'm working for DLR now for about 15 years in the field of CSP. The first part of my work was dedicated mainly to the Stirling systems. Now I'm also working on tower technologies and other areas. First of all, I want to introduce the components of a dish Stirling system. The main component is a concentrator and a tracking system that enables you to point the concentrator towards the sun. In the focal area, a Stirling package is placed, which works as a power conversion unit. For the movement of the whole system, we need a control system. In principle, there are two tracking systems available for tracking the sun. The first is a polar tracking system, which is composed of a rotation axis that has to be perpendicular to the sun's movement during the day. This axis has to be tilted during the seasons because, as you know, the sun in summer is higher than in winter time. The second possibility is a so-called azimuth elevation tracking system. Here we have a more complex movement with one rotation axis perpendicular to the surface and another axis that is tilting the concentrator upwards. In the next slide, you can see an example for a polar drive system. It's the Distal 1 system that was built at the PSA. The red line is the polar axis, and you can imagine that you can turn the whole concentrator setup around these axes. And during the seasons, we have to tilt these axes upward or downward. So we have two drives. One is the polar drive, which is the daily drive. We have to turn the concentrator with a constant speed of 15 degrees per hour. And then we have the seasonal drive, where we adjust the tilt of the axis during the year. An example for the azimuth elevation drive is the Eurodish system here on this slide. We have the two axes, the red lines. There's one which is vertical, the rotation axis, the card that is turning around these axes. And then we have the elevation axis, where the concentrator with the Stirling package is just tilted upwards. We need a more complex control system to control these movements, which is calculating the current position of the sun and points the concentrator to this position. In this slide, I want to introduce some important parameters and characteristics of parabolic concentrators. In the picture, you can see a parabola. The light is coming from the right side and is reflected at the surface towards the focus. Parameters that are widely used in the literature are the F/D ratio, which is focal length to diameter, and the rim angle, which is the opening angle looking from the focus towards the parabola. When we are talking about errors, we can divide into slope error. When the curvature of the surface is not the desired one, we can experience a misalignment of facets when we have a faceted concentrator design, and we can find non-specular reflection on the mirror surface. Other errors can be introduced from the tracking system, and of course, we have to consider that the sun is not a point light source. In the upper formula, we can see the relation between the F/D ratio and the rim angle. The second formula is a mathematical description of the parabola. Concentration ratios are widely used to describe the quality of concentrators. We find ratios using the flux densities in the focal area in relation to the flux density of the sun in the mirror aperture. Or we can define a geometrical ratio using the size of the focal area in relation to the aperture size of the concentrator. As already mentioned, we have different concentrator designs. There are concentrators with a continuous shape, and there are many designs using facets to achieve a parabolic surface. In the left side, you can see an example for a concentrator with a continuous shape made of a stretched membrane. And on the right side, you can see a faceted concentrator using the same stretched membrane technology. The purpose of the parabola is to concentrate sunlight in the focal plane. We use so-called flux maps to describe the flux distribution on a surface. In the left figure, you can see the flux distribution of a parabolic concentrator in the focal plane. On the axis, you can see that we can reach 10,000 times the intensity of the sunlight, and even more depending on the quality of the dish. In the right figure, you can see the intensities in an area behind the focal plane, where we normally place the absorber of the Stirling engine. The energy density in the focal plane is too high and we would burn the material of the receiver immediately. That's why we have to place it in an area with lower flux densities. But as you can see in the right figure, the flux densities in the receiver plane is not as regular as we would like. The most important quality criteria of a concentrator is the resulting flux distribution on the receiver plane, which should be as even as possible. Now I want to introduce the main components of the Stirling package. First of all, we need a Stirling engine, the power conversion unit that converts the heat in mechanical power. We need a heat exchanger to introduce the heat in the Stirling process. This component we call receiver, and in most systems it is placed in an isolating housing that we call cavity. To convert mechanical power into electricity, we need a generator that is coupled to the Stirling engine. To get rid of the excess heat, our package is equipped with a cooling system, and of course we need a control system for a safe operation of the engine. To explain the functioning of the Stirling engine, you should first know its main components. The schematic engine is composed of 2 cylinders with their pistons, 2 heat exchangers, one for cooling and another one for heating, and the central component is a regenerator, which is a storage device for heat. The component not mentioned yet is the working gas that is enclosed in the engine. In the right figure you can see the 4 states in the theoretical Stirling process. In the first state, the working gas is on the left side. The side is the cold side of the engine. Now the left piston starts to move right and the gas volume is reduced. We talk about the compression, and from thermodynamics we know that the temperature of a gas increases when it is compressed. To avoid a temperature increase and to achieve isothermal compression, we take out heat from the volume with our gas cooler as shown in the second state. Then the right piston starts to move right, while the left piston continues to move. The working gas moves through the regenerator to the right side. Because the regenerator is hot, the gas temperature increases drastically. We call this state change isochorous displacement. Now the left piston stops, but the right piston keeps moving. The volume enclosed increases, what we call an expansion. From thermodynamics, we know that the gas temperature would decrease, but we introduce heat from the heat exchangers to achieve an isothermal expansion. Finally, both pistons are moving to the left side. The hot working gas is pushed through the cold regenerator where the heat is stored for the next cycle. The temperature of the working gas is returning to the low level and we start with the next cycle. We can take out mechanical power from the cycle because we have to introduce power for the compression of the cold gas. But we get out much more power from the expansion when the gas is hot. For completeness, you can see the PV diagram and the TS diagram describing the process on the left side. In this slide, you can see the position of the piston during the cycle. The red line is the movement of the pistons in a theoretical cycle, and the blue line describes the movement of the piston in a real pneumatic engine when the pistons are connected to a crankshaft. The piston movement is describing a sinus and there's a phase angle between the movement of both pistons. In this slide, you can see different types of Stirling engines. The upper setup is very close to the theoretical cycle. This type is the alpha type Stirling engine. Below, you can see a schematic for the beta Stirling engine. The working gas performs the same stage changes, but there's one piston for compression and expansion, and the other one is just responsible for the displacement of the working gas through the regenerator. In this slide, you can see a section of a real Stirling engine with all the components. The regenerator is located in the foot of the heater. The left side is the hot side with receiver and expansion cylinder, and the right side is the cold side with gas cooler and compression cylinder. The crankshaft is defining the movement of the pistons. In this slide, you have animated graphics describing and showing how the pistons are moving in a real engine. In the following, I would like to show you the Stirling systems that are available or that have some historic relevance. Since the number of engines is limited, I will order the system by the engine they are using. Available engines or important engines are the United Stirling AB 495. There's also a Stirling engine that was developed by Stirling Thermal Motors. Another engine is the Stirling V160. There's an engine developed by USAB, the V160 Stirling engine that was later taken over by Solo and today is manufactured by Cleanergy. There's an example for a free piston engine developed by Cummins Power. The first engine that I want to introduce to you is United Stirling AB 495. It is a kinematic engine. It has 4 cylinders, 4 times 95 cubic centimeter displacement volume. It is an engine that is using double action. I will explain that later. It has 25 kilowatts electrical power and using hydrogen as a working gas. Normally, it is operated at a maximum temperature of 720 centigrades and 20 megapascal of pressure. The thermal efficiency is 41%. The first system using this engine is the Aramco Vanguard system built in 1984. The diameter of the concentrator is 10.5 meters. It has an aperture surface of 86 square meters. It has 336 facets of silvered glass mirrors. It has a very heavy structure, more than 10 tons. It has an eccentric tracking system that is actually the cause for the very heavy structure. It uses, of course, the 495 Stirling engine with 25 kilowatts. The solar to electric efficiency is about 30%. The next system I want to introduce, which has really a big relevance, is a system developed by McDonnell Douglas. The first prototype was built in 1984. It has a diameter of 10.5 meters. Aperture surface is 87 square meters. It has only 82 silvered glass mirrors glued on a bent back structure. It has a much lighter structure. It has an azimuth elevation drive system, an engine, of course, the 495 with 25 kilowatts, and it has a solar to electric conversion efficiency of more than 30%, which was a record that was demonstrated in 2007 by Sandia National Labs. On this slide, you can see a short video showing the movement of the system during the day. In the morning, the system goes on sun on the east side and continuously tracking the sun, moving both axes up to the evening and then returning to the parking position. The development of the system was bundled in the company SES, Stirling Energy Systems, together with the project development company Tessera Solar. These companies tried to introduce the redesigned system into the market. It then was called Suncatcher. On the slide you can see the cost goals that they wanted to reach through massive mass production using production methods from the automotive industry. The picture shows their demonstration plant in Phoenix, Arizona, where they mounted 60 systems producing about 1.5 megawatt. On this slide, you can see a list of projects that are approved in the southwest of the US. Here you can see 2 big projects that were acquired by the Tessera Solar to be built with the Stirling system. Altogether, 1.5 gigawatts of the Stirling system were planned in the southwest of the US. But the company first sold their big projects, and finally, at the end of 2010, both companies disappeared because of bankruptcy. On this slide, you can see a Stirling system that was built using, let's say, the big brother of the 495. It is a 275 engine with 50 kilowatts. It was built by the company Schleichbergermann and Partner, SBP, in Saudi Arabia in 1986. The diameter is 17 meters, aperture surface is 227 square meters. It is built with a stretch membrane technology, uses back silvered glass mirrors glued on the stretch membrane. It uses a turntable and it has an efficiency of about 23% conversion from solar to electric power. The next engine is the engine developed by the company Stirling Thermal Motors, STM. It has a very special design because the pistons are not connected to a crankshaft. The drive mechanism used for this engine is so-called swash plate. In the lower figure, you see the pistons in a line. Normally they are in a square setup. Here you can see it in a line. I want to explain you what means double-acting engine. This means that between every piston and the next piston, there's one Stirling process running using the volume above one piston as a hot volume. Then we have our heater, our regenerator, and the gas cooler. And then the volume below the next piston is the compression volume of these process. So we have 4 pistons and we have 4 Stirling processes in parallel. Now you can see the pistons moving. Of course, there's a phase angle between these movements. And now you can see how these pistons are located in the real engine. It is a square setup, and you can see that the movement is controlled by a swash plate, which is moving at the lower part of the pistons. Since the angle of the swash plate can be changed, even the oscillation of the pistons can be changed. Good. This engine has power also of 25 kilowatts electric. Normally it's using hydrogen as working gas. Operation parameters are similar to the former engine, 720 degrees gas temperature, but at lower maximum pressure. 120 bars is the maximum pressure that is allowed for this engine. The conversion efficiency from thermal to mechanical energy is 40%. The company STM, together with SAIC, developed a dish that is using this engine. This is the only dish system using this engine. It has a diameter of 10.4 meters, a purchase surface of 84 square meters. At the beginning, they were using stretched membrane concentrators, facets, using an acrylic film. Later, this acrylic film was replaced by steel membranes with glass mirrors glued on the front side. It has 16 facets. Each facet is a stretch membrane facet that has a vacuum system. The vacuum inside these facets defines the concentration of each facet. The drive system is azimuth elevation. We have a rated power of 22 kilowatts electric and a solar to electric conversion efficiency of about 20%. The next engine was also developed by United Stirling and later redesigned by the company Solo, which is a German company. And today the company producing this engine is Cleanergy Industries. It is a kinematic engine with 2 cylinders. It has a displacement volume of 160 cubic centimeters. The power of the engine is 10 kilowatts electric. It can use hydrogen or helium as working gas. Operating parameters are 650 centigrade gas temperature and a maximum pressure of 150 bars. The conversion efficiency from thermal to mechanical power is about 40%. The first system I want to introduce using this engine was built in 1991 by SPP on the Plataforma Solar in Almeria, Spain. It has a diameter of 7.5 meters. A purchase surface is 42 square meters. It's using stretch membrane concentrator with black silvered mirrors glued on the front side. The tracking system is a polar drive system, and in the case of Distal 1, it was using helium as a working gas. The efficiency was about 20% conversion from solar to electric. Since Distal 1 system was quite successful, the same company, SPP, initiated the next project. It was called Distal 2. The systems were built up in 1997 on the PSA also. Diameter was increased to 8.5 meters. A purchase surface is 53 square meters. It's using stretch membrane technology for the concentrator with back-silvered glass mirrors on the front side. The drive system was changed to azimuth elevation, now using turntable concept that was developed by the company. Of course, the engine is now the redeveloped Solo Stirling 161 with a rated power of 10 kilowatt electric. Since the concentrator is enlarged, the maximum power can already reach at 850 watts per square meter. Working gas is helium. Solar to electric efficiency is about 21%. The last generation in this row was the Eurodish that was developed or built up in 2001, also at the PSA. Diameter is the same as distal 2, 8.5 meters. Aperture surface is 53 square meters. The concentrator concept was changed, now using fiber reinforced plastics with back silvered glass mirrors on the front. The tracking system Azimut elevation using the same turntable concept as the former generation with some optimizations. The motor is a Solar Stirling 161 with a rated power of 10 kilowatt electric. Also, this can be reached at 850 watts per square meter. At the beginning, the systems were operated using helium as working gas. Later, they were changed to hydrogen, which is a more efficient gas, then reaching about 24% of efficiency for the conversion from solar to electric. Another system using the same engine was developed and built up in 2000 at Sandia National Laboratories together with the company WGA with a diameter of 7.5 meters, aperture surface 41 square meters. They're using facets made up of sandwich of sheet metal and an aluminum honeycomb using silvered glass mirrors on the front side. Tracking system is Azimut and elevation. Engine, of course, the Solar Stirling 161. Rated power 10 kilowatt electric that is reached at 1000 watts per square meter. They were using hydrogen from the very beginning, reaching already a high efficiency of 24% solar to electric conversion. The next engine I want to introduce is actually a representative for another engine class. Now we have an example for a free piston engine. The movement of the pistons is not defined by a crankshaft. The pistons are just held by spring systems that are limiting the movement of the pistons. On the left side, you can see the working piston of a beta Stirling engine, which is coupled directly to a linear generator. On the right side, you see the displacement piston, which is moving the working gas through the regenerator, which is integrated in the heating head. The Cummins three-piston Stirling engine was a 6 kilowatt Stirling engine using helium as working gas at a maximum temperature of 630 centigrades with 4 megapascal of pressure. The conversion efficiency from thermal to mechanical power is 33%. Cummins also designed a dish system for this engine. There's only one prototype, was built in 92. The diameter is 7.3 meters, aperture surface 41 square meters, 24 stretch membrane facets with aluminum coated plastic film. It used a polo drive system for the tracking. Another Stirling system that still has a high importance for the technology is a rather small system developed by the American company Infinia Corporation since the year 2007. Before their solar activities, the company used to develop and build very small free-piston engines for space applications that were able to run for many years without any need for maintenance. Infinia's solar concentrator has a diameter of about 4.5 meters. The first prototypes used a concentrator made of fiber-reinforced plastics with thin glass mirrors bound to the front side. The system is tracking the sun using an Azimut elevation drive system. The engine is a free-piston engine with a rated power of 3 kilowatt electric. The system is prepared that waste heat from the engine can be used in combined heat and power applications. About 6 kilowatt thermal power can be made available for such applications. The system has an efficiency of about 24% for the conversion from sunlight to electrical power. The system is currently the last commercially available Stirling system. Infinia has a strong collaboration with the Spanish development investment company Renovalia. Together, they developed the second-generation system, changing many components and heading strongly for the application of automotive production methods to reduce the cost of the system. The companies built their first demonstration plant close to Albacete, Spain, with a planned power output of 1 megawatt. The companies have applied and were accepted for the construction of several plants with a total power of 71 megawatts in the Spanish feed-in tariff. On the next slide, I would like to talk about the experiences from the operation of the Stirling systems. We will have a short look on the typical operation behavior. We will make a breakdown of the losses during the energy conversion chain of a Stirling system. We will have a short look on the economics, and I will give you a short outlook on possible improvements of the Stirling systems. When we want to calculate the output of a Stirling system, we need to know the characteristics between the solar input and the electrical output. As you can see in the chart, this characteristics is almost linear behavior. The system starts to produce power at an insolation level of about 300 watts per square meter, and from this point the power output increases proportionally with the increase of direct normal insolation. Most Stirling systems are designed to reach the maximum power at an insolation of 1000 watts per square meter, but in this particular graph you can see the characteristics of a system with an enlarged mirror that reaches the maximum power already at lower insolation. The idea to increase the concentrator size is to increase the full load hours of the system during the year, because depending on the site there might be only very few hours where the insolation reaches the design value of 1000 watts per square meter. We stay with the typical operation behavior of the Stirling systems. Here you can see a normal operation day with good weather. The yellow line is the direct normal insolation going up in the morning of an almost perfect operation day. The blue line is the output power of a Stirling system, and you can see the output power follows perfectly the input power. On the other chart, you can see what happens when we have fast changes in the input power. Again, the yellow line is the direct normal insolation, which in this case has fast oscillations, but you can see that the blue line representing the electrical power is following immediately. The time constant that describes the system's reaction on changes on the input side is smaller than 90 seconds for many Stirling systems. With this slide we want to have a little bit closer look on the system costs for Stirling systems. Here you can see the contribution of the components to the total costs. The costs are divided into Stirling engine, electrics, concentrator, machine parts and simple steel parts. Furthermore, you can see the production cost decreasing with higher production rate, which is quite logical. Please don't pay too much attention to the numbers, because production costs are varying very much between different systems, and this just be an example. On this slide we can see the development of electricity costs for different production rates and for different generation systems. Again, please don't pay too much attention to the absolute costs. These numbers are changing very fast and are not correct anymore, especially for the PV systems, also included in the graphics. You can observe the generation cost for the electrical power produced with the Stirling system depend on the site you place the system and of course on the production rate. We see that at increasing manufacturing rates, the electricity costs can drop easily below the generation costs for small diesel sets in remote areas, where the diesel costs highly depend on the transportation costs to the remote area. This should demonstrate that there is a niche market for rather small Stirling systems in remote areas. On this slide, we want to have a short look on the losses in the power conversion chain of a Stirling system on the example of a SPP 9 kW system. We start with 100% solar radiation from the sun. Not all radiation is reflected on the mirror surface, even if we have a completely clean mirror. We lose a minimum of 6% of the power due to the reflectance of the mirrors. The next loss comes to errors in the shape of the concentrator. Not all light that is reflected from the concentrator surface will enter the aperture of the Stirling package. Then we have optical refraction on the receiver surface, we have radiation and convection losses out of the aperture, and we also have some heat conduction losses through the cavity walls. The biggest loss in the whole conversion chain we can find in the power conversion unit. Also, the theoretical Stirling process has the same efficiency like the Carnot process. The conversion efficiency from heat to mechanical power of a real engine is quite higher. The electrical generator also has some losses for the conversion from mechanical power to electrical. Finally, the Stirling system has some parasitic power needs for the drives, the cooling system and the controls, and we can see that only 20% of the solar power is available to be supplied to the electric grid. The maximum conversion efficiency of a Stirling system was demonstrated by the system of SES to be more than 31% at the Sandia National Test Site. On this side, I want to introduce some possibilities how the performance of a Stirling system can be improved. On the left you can see a so-called flux map of the concentrator. The different colors represent different flux densities of the concentrated sunlight on the receiver surface. Measuring the flux densities in different planes between the focus and the receiver surface allows to optimize the cavity and aperture geometry to reduce the thermal losses out of the aperture. The gray surface on the right is the original geometry of the cavity, and the dotted line shows the adapted geometry after such an optimization process. In this case, the diameter of the aperture could be reduced by more than 20%. Another way to improve the Stirling systems is the possibility to hybridize the system. In this case, the same PCU can use a burner system as a second heat source. This burner might be operated in parallel to the solar operation in some cases, or especially during cloudy weather and during the night hours. On the slide you can see two approaches to realize such a hybrid system. The left receiver is using a heat pipe to transport heat from the solar absorber or from the burner system to the heat exchanger of the Stirling engine. In the right figure you can see the design for a ceramic receiver that can be heated by the sunlight from the front side or from a so-called porous burner system from the back side. With this slide, I want to come to the end of my presentation. We want to thank the funding organization that made possible the creation of this video tutorial. Thank you very much for your attention.